Hello, this is Logan Chipkin, and you're listening to the Fallible Animals podcast. I have a very exciting treat to share with you today. Several months ago, I interviewed Dr. Chiara Marletto of Oxford University. She's a physicist who has been working on developing and applying constructor theory for several years now. I'll link to a few of her publications in the show notes page. She's published papers such as the constructor theory of information, constructor theory of life, and constructor theory of thermodynamics, and a few more, all of which I'll include in the show notes page. So I interviewed her with the intention of doing something with the transcript of the interview, but I figured now that I have this podcast, I might as well just publish the audio file to all of you good people. It's a very wide-ranging discussion in which we talk about the origins of constructor theory, the theoretical tools that I spoke about a little bit last week, and a bunch of other topics that I really recommend, including rebuttals to potential criticisms of constructor theory, which is always important to understand. Two brief disclaimers before you listen to the entire interview. One is that I recorded this, as I said, several months ago, and it was before I had a microphone, so please pardon the audio quality. And the second disclaimer is that since I was never actually planning on using this audio file for audio purposes, I don't make any attempts for this to be a conversation. It really is just me tossing up softballs for Chiara to knock out of the park. And that's exactly how it comes off. But nevertheless, I think you'll still enjoy it. There's a wealth of knowledge. Chiara is absolutely fantastic and erudite in all of her explanations. And without further ado, I give you my interview with Chiara Marletto. Okay, so before I ask about your own involvement and how you got into constructor theory, could you please tell me a little bit about just what is constructor theory?
So constructor theory was originally proposed as a program by David Deutsch, 2012, and so he wrote this paper which was mostly laying the philosophical foundations of the theory, and the program was to try to recast the whole of physics in different terms. So instead of using these dynamical laws plus initial condition type of approach, David suggested to use an approach which is rooted in the quantum theory of computation, but extended to the rest of physics. And the approach is to use statements about what tasks are forbidden, are impossible, and what tasks are possible, and stating also why. And I think this was also, in a sense, a very ambitious program. At the time, David outlined various possible applications, but basically what happened is that since then, when we started working on it together, we realized that the theory had actually a much more wider applicability than it originally looked like. And so we started actually, so that's how I came in, applying it to various problems that are open in quantum information, in quantum thermodynamics, and in the foundations of quantum physics and so on. And I think, so therefore, since David started the theory, a number of problems have been addressed with this theory. And as we were going along, a number of new problems emerged. So I think now the program has been revised and it's become, in a way, even more ambitious. And what's going on now is that some people are getting interested in this, and largely also thanks to what I did in terms of developing the theory and applying it to various things. Turns out there are actually even some practical experimental demonstrations that can be realized, and that's what we are working on at the moment. At least that's part of a number of proposals that I'm putting forward to continue this research. So I think it's kind of growing momentum, and there is a lot of excitement around these ideas. And of course, the community is, as usual, it's got a sort of inertia before it starts picking up some tools. But I think as far as researchers I've been talking to directly are concerned, we're trying to bridge ideas from constructive theory into ideas from current efforts in quantum thermodynamics, in quantum information. So we are building connections, and in a way, this is going to provide some more powerful tools even for those fields. So I think we are at the moment where there is a sort of interchange of tools between those tools of constructive theory and tools of existing disciplines that are more established and mainstream. So that's quite exciting as well. I hope this answers the question.
Yes, definitely. And we'll actually get back to other scientists getting into constructor theory, because I definitely want to ask a little bit about that later. But briefly, so you are located right now at Oxford, yes?
Yes, that's right. Yes.
And then if you'd like to elaborate, but you don't have to, may I ask how you got involved in constructor theory in the first place? And I ask because it strikes me as an outsider as just there was one person working on it and just published a paper on it, and then you got involved. I'm just curious how that happened.
Yes. So I think, well, when David published this paper, I was doing my PhD in Oxford.
Okay.
And I was working on quantum information things. And at some point, I came across this theory, and it actually turned out to be a thing that I identified as a very, very promising tool to solve some problems that I've been stuck with for a while, in a sense that I was interested in understanding, for instance, I was interested in von Neumann's theory of the universal constructor, which was connected to issues in biology, theoretical biology, and quantum information, because of course people in quantum theory were, the founding fathers actually were interested in trying to find, like von Neumann, were interested to find the ultimate implications of quantum physics, because they realized how powerful and far-reaching the theory was. And it's very interesting that von Neumann, who could master the foundations of quantum physics so well, also wrote very extensively about these more computational and foundational issues about what would it mean to have a universal machine that exceeds the powers of a universal computer. And this would be the universal constructor. It's a generalization of the universal computer as Turing envisaged it, to not only being capable of performing all the computations that are physically allowed, but also all the tasks that are physically allowed. So not just computations, but generate tasks like cooling down a mass of water from a certain temperature to another with given resources and so on. And von Neumann had this nice set of writings that I was reading into at the time. And as soon as I saw constructor theory, I noticed that it would actually allow me to connect those kind of problems that I was interested in with the foundations of quantum information and the foundations of thermodynamics, which were things that I was really interested in. And this is a long-standing interest of mine. So that's it. I approached David, and we started discussing, and then in the end we decided to write a paper together, and this was during my PhD. So my PhD thesis ended up being mostly, maybe 1/3 of it on some standard quantum information things, and the rest was on constructor theory. And then colleagues, you know how it is in research, you just follow problems how they come up, and turned out that there were more problems than I anticipated in the theory, and so I suggested that we put it on more solid grounds first, and then we try to apply this scheme to some open problems so that we could show to the community also that this is a viable scheme that works and so on. So, and I think that's what I'm doing at the moment. So what happened basically is that I opened up some unrelated new independent line of research, and they grew within this framework of constructive theory, and that's what I'm doing right now.
I'm always curious how what I perceive as fruitful research had its foundation. So thanks for elaborating.
Yeah.
So, okay, you spoke a little bit about why constructor theory was developed in the first place, but could you tell me what the underlying motivations were for its genesis?
Yes. So in physics, I think, if you look at physics from at a distance, you will see a very successful enterprise with universal theories being conjectured, like first Newton's laws of gravitation, which was the first kind of universal theory that was ever proposed. Universal meaning that it applies to everything there is in the universe. And then Einstein and various other scientists, the founding fathers of quantum physics, proposed an improvement of that theory to cover things that it didn't actually cover, and this happened at the start of the 19th century. And there is one thing that all of these things, all of these approaches, all of these theories have in common, which is that they they try to explain the whole of what's going on in terms of these dynamical laws, so trajectories, predicting where an object goes in space and time, given what the initial conditions of the object. And this applies to the whole universe, in fact. However, there are also other kinds of principles and laws that have been conjectured, which seem very powerful. And these have a different approach. So they don't have a dynamical law or a law of motion, but they are formulated like the principle of thermodynamics, the conservation of energy, and also more recently, these laws of quantum information. They're formulated in terms of statements about what transformations are possible or not, given certain resources, let's say. So, for example, conservation of energy obviously says that energy can't be modified for an isolated object. So you can only increase it or decrease it if you couple this object to a source or a sink of energy, because overall the energy has to be conserved. And this is a statement that doesn't really mention dynamical laws, although you can prove it given a particular dynamical law. And we know that all dynamical laws we have at the moment satisfy this principle, and hopefully future laws will too. And so with thermodynamics, you got the second law, for instance, and there you start seeing there is a problem, because actually the second law is very powerful and works very successfully for macroscopic objects like heat engines. This was Clausius and founding fathers of thermodynamics type of problems. They were trying to address the question of how do we build a locomotive for a train, and let's try to figure out how a steam engine works and so on. But these are macroscopic objects. And if you try to extend the second law to microscopic systems, meaning a single, let's say, molecule doing something like a sort of cycle, you try to define a heat cycle for a single molecule, then you run into all sorts of problems, because the laws of thermodynamics are not suited for these microscopic objects. They just don't translate. It's unclear what they say about microscopic systems. And even the statistical mechanics approach with Boltzmann and so on holds only in certain limits. So, for instance, for many systems being involved in the interactions. So there are all sorts of approximations that you have to make in order for the second law to apply. And if those approximations are not satisfied in your system, you don't know what the law says. So that's a problem. And I think constructive theory, one thing it would like to solve is to put some of these laws that only seem to apply to macroscopic entities and yet are very successful in that domain, to put those laws on firmer grounds and to state them in a way that they are scale independent. That's one thing, therefore. Another thing is to formulate new laws about entities that have been so far very useful in terms of understanding the physical world, but these entities don't really have a unified theory about them. And this is, the information is particularly one of these entities. So at some point we realized that information is not independent from physics. So entities that can carry information, which entities can carry information is decided by the laws of physics. So you have an object and you want to decide whether or not it can carry some bit of information. That actually depends on what interactions it can have with its surroundings, whether it can be put in one or two states, let's say, that are distinguishable and so on. And these concepts, distinguishable, whether it's possible to permute the states of the object and so on, all of these things are decided by the laws of physics. So there is very intimate connection between the fact that information can be instantiated in the physical world and the way laws are. However, the theory of information that currently we are using to, for example, design the quantum computer and so on, is not as general as it should be, because it's using various details of quantum theory. Quantum theory is a dynamical law and is only specifically applicable to quantum systems. However, you would like a theory of information or quantum information to be more generally applicable in a way that concepts like entanglement, copy operations, cloning, various other things like that can be defined and explained irrespective of the particular model that you have for your system. And why is this useful? Well, the reason is that likely quantum theory is not the ultimate theory, because we know it clashes with GR, with general relativity. So there will be a better theory behind quantum theory, but it's also possible and likely that this new theory will still allow phenomena like entanglement of particles, like quantum computation and so on. But if we don't have definitions for those that can be applied to systems that are not quantum, how are we ever going to understand these new systems, etc.? So I think the second aim of constructor theory is to put on solid grounds a theory of information, which can define all of these concepts and the laws that information follows, irrespective of the dynamics of the physical systems that we are considering, but only based on certain general principles such as locality, such as certain principles to do with the interoperability of information and so on. So second aim is, let's put on solid grounds a theory about entities that seem to be significant at the moment in physics, but of which we don't have such a theory. And one of them important is information. Another one is work and heat, but this kind of falls in the first category. Finally, and this is a very long-term kind of ambition, is can we actually show how dynamical laws and initial conditions actually follow from these principles? So suppose the constructor theory works, and we've got this set of principles that augment the theory of thermodynamics, the theory of information that we currently have. Is it possible to change the way we formulate laws of physics in a way that actually the dynamical laws follow from these principles rather than the other way around, which is what we're doing now? And well, we don't know the answer, but I think one of the scopes of constructor theory is also to show how dynamics and time can emerge out of these timeless principles and constraints. And this would address an open problem, which is kind of at the heart of theoretical physics at the moment, which is that there are all sorts of theories about cosmology. I'm no expert about them, but that there is a thing that even a non-expert can grasp about them, which is that they have a problem, and the problem is to explain the initial conditions. So, let's say you want to say, I want to explain what I see now in the universe by giving an initial condition and some laws of motion. That's the logic that they all follow, these cosmologies. And then you state the initial condition. And of course, the problem is that the initial condition has to be not a generic one, but it's got to pertain to a set of possible initial conditions. And then you have to explain why that set and not another. And it's not good to say, oh, I have to choose this one because I have to explain, this is the only set that explains what I see now, because that's a bit of a circular explanation. You may actually as well explain the initial conditions in terms of the conditions of the universe now. And this seems like a kind of circularity. And this is a theme that even inflation, which is probably one of the most followed theories at this stage, cannot quite address. So I think it's possible, but of course this is extremely very far in the future in the speculation, but it's possible that constructor theory provides a way out of this problem. But I think David and I and other people who work on this are quite behind in terms of, we haven't worked out yet even the theory of dynamics in constructor theory, so which is one of the new lines of my of one of these proposals that I've just been finishing writing. So I think I hope this answers. So there are three things, and those are the three main things about constructor theory, I would say.
Yes, definitely. And later I'll ask you about your current research. So that sounds interesting. So you mentioned a little bit about constructor theories about in terms of what's possible and impossible. Could you please elaborate as in much detail as you want about what exactly are the theoretical concepts that are used in constructor theory?
So the theoretical cards are so the main concepts in constructor theory are two things. One is tasks, and the other one is a constructor. However, the fundamental things are tasks, and constructors are there only to be removed in a way. So I'll explain in a second. A bit like what happened with the theory of relativity, which is actually the theory that says that there are no absolute time and space, but actually it's So I think the theory of relativity in the name has the same sort of thing about constructors. You have to remove the notion of constructors from constructor theory in order to get the theory. So I'll explain what that means in a second. So let's start with a task. A task is a set of ordered pairs of input-output attributes of a physical substrate. And a substrate, you can think of anything that can be changed by appropriate action of the environment. And so, I mean, familiar examples of tasks are negations. So, 0 goes to 1, 1 goes to 0 is a computation, is a bit flip, and that's an obvious example. Another example of a task is to, as I was saying, cooling down a certain mass of fluid from certain temperature to another temperature given certain resources. Another task could be lifting a weight in a gravitational field. Another task could be creating entanglement out of no entanglement, and so on. So the task is just specifying a putative transformation. And then this transformation can either be possible or impossible. And there are no things in between. And by impossible, we mean that the laws of physics have a fundamental limitation to how accurately this task can be realized with systems in physical reality. So, for example, changing the energy of an object from certain value to another value is an impossible task because of the conservation of energy. So if you try to do that without ever using anything of your environment, so you just operate on your system, this is clearly impossible because there isn't any energy source or sink there, and the energy can't be changed. So actually, the accuracy to which you will perform that task is very low because your initial state, let's say you want to raise a weight in a gravitational field without using any energy from outside, your initial state of the weight won't change just because it's decoupled from the rest of the environment. So that is an impossible task. However, you can achieve the net effect of changing the energy of a system by having some side effects on the environment. And then, so the overall task of transferring, let's say, the energy of the weight in a gravitational field to a flywheel, let's say, that starts moving as the weight goes down if it's appropriately connected, that's a possible task because it can be achieved to arbitrarily high accuracy by setting up the appropriate thing. So impossible means we can't achieve it with arbitrarily high accuracy and no other side effects in the universe. And so that's impossible. Possible means that we can do that. And so the fact that you can achieve a transformation on a system with arbitrarily high accuracy with no other side effects in the universe means that somewhere in the environment there is an entity, which is the constructor, which acts like a cycle. So it gets in input the substrate in the input states of the task. So let's say the state 0, and the constructor does something to the system, spits it out in the state 1, and it stays approximately unchanged. So it operates in a cycle in a way that if you want to feed a new system with the new state 0 in, it will still deliver it in the state 1 reliably. However, to say that the task is possible, you don't have to enumerate all possible constructors that could perform the task. The idea is to avoid talking about the constructor and its explicit design in the theory, but just state the laws as requiring that a certain task is possible or is impossible and working out the consequences of that, without ever having to specify the particular design of the constructor when we're talking about a possible task. And this is important because for most tasks that are performed in the universe, the constructor is highly complex. Just think of a computer, it's as close as it gets, let's say, to an accurate performer of, let's say, a NOT gate, and it's very complex. And the fact that we can abstract constructors from the laws of physics and just talk about the possibility of tasks and working out consequences is one of the powerful switches in constructor theory. So tasks and possible tasks, as well as impossible tasks, have an algebra. And I think what's going on at the moment is that there is a mathematician who is working on formalizing constructor theory properly in a way that's kind of even more mathematically grounded. So I think this is some recent development that is very nice. But basically, the tasks as it's the algebra of tasks as it's formalized now is the recipe to combine tasks in parallel, in series, and working out the consequences of the fact that some task is possible for other kinds of tasks. So for instance, if two tasks are possible and you take the parallel composition, what happens? Well, there is a law in constructor theory that says that the composition of two possible tasks must be a possible task, and that's one principle that constructor theory has. It's a composition law. And the algebra of tasks has to mirror these constraints. So whatever group or more generically algebraic structure you will define with tasks has got to mirror these physical constraints. And most of the theorems we've proven so far are based on set theory and these basic definitions of tasks as sets of or ordered pairs of attributes. However, we are hoping, and this is the work of this mathematician that we're doing in collaboration with him, that there'll be an even more sophisticated way of talking about tasks, perhaps using category theory or perhaps using some other kind of algebraic structure. But this should make the theorems even more powerful and grounded and rigorous. Yeah, so I hope this answers your question.
Yeah, definitely. I didn't know there was a mathematician in the field now, as it were, so that's cool.
Yeah, it's nice. Yeah.
I look forward to that paper. Okay, so you had talked a little bit about the successes of constructive theory in unifying some ideas in information and quantum information. So could you tell me about some early successes in quantum theory? Feel free to talk about information or anything else.
Okay, so right, so so I think the first success was a combined action of this paper that David and I wrote on the constructive theory of information and my paper on the constructive theory of probability. So I can summarize what this boils down to. So as I said, the information theoretic structure that emerges out of quantum theory is very rich, and it's something that is independent of certain details of quantum theory. So for instance, when you talk about entangled particles, which is of course a quantum phenomenon as far as we know, the entanglement, the fact that two things are entangled, is a purely information theoretic concept. And that means that it's independent of a vast majority of details of those two systems. For instance, if you can entangle a photon with another photon, but you can entangle also a photon with an atom, and they will be entangled to some degree, irrespective of the fact that one is a photon and the other one is an atom. And likewise for other physical systems. Therefore, this suggests that it's possible to free the quantum theory of information of the reference to specific quantum dynamics things. And this is something that hasn't been done yet in the literature, because most of the theorems in quantum information theory are using the dynamical laws of quantum theory to show what they show. So for instance, if you talk about the channel capacity in quantum theory, you do need the quantum dynamical laws to show what the capacity of the channel is, etc. So the work with David put some seeds down to define a theory of a unified theory of classical information and quantum information that does not use any specific reference to the dynamics of the systems that are involved. And this is cool because we expect that the future theories that will come after quantum theory, which necessarily will come because, as I said, quantum theory does not quite work properly with GR, which means that both probably are going to be improved into a better theory. So this means that the theory we have, if we define a unified theory of information which kind of underlies both classical and quantum systems, and also potentially other systems that don't obey quantum theory but have the same information theoretic properties, then we'll be able to answer questions like, is there a different type of dynamical law that supports the same quantum information processing power as quantum theory, but is not quantum theory? And that's actually useful because it seems to point into the direction of where to look for the successor quantum theory. So that's one important applicability of this theory that we are constructing. And so in the paper with David, we came up with a number of results which basically show under what conditions you can get all the qualitative properties of quantum information out of principles that are not based on particular details of the dynamics. So therefore, they're very general information theoretic principle. In particular, there's one which is called the interoperability law for information, which sort of formalizes the informal idea that information can be copied from any system that can embody information to any other, irrespective of the details. But constructor theory expresses it very elegantly. And these are qualitative properties. So this means we can talk, let's say, about entanglement in a rudimentary way. So we can say, let's say, that something is entangled or not, but we can't quite say to what degree something is entangled, which is, of course, very important to make predictions. So that's kind of missing in that paper. What the constructor theory of probability did, which is my follow-up paper, is to define a set of theories a set of conditions for dynamical theories that guarantee the fact that they display the same probabilistic quantitative structure as quantum theory. This doesn't mean that I worked out a particular theory like that. I've just defined the space, let's say, of such theories by giving some sufficient conditions. So, you can imagine a space of possible theories. There's quantum theory somewhere. There is you can imagine a Venn diagram, something around it, like a blob. And this blob is defined by these principles that I give in the constructor theory of probability. And if you pick a theory in that set, of course, we don't have any conjecture theory now, but the idea would be to pick one theory in that set. It will have the same quantitative structure as quantum theory, but it will be a different theory. And so basically these two papers combined give a framework for local deterministic theories, which could in principle generalize quantum theory. And that's nice because, and this is the development that I'm developing now, this is useful in all sorts of situations. And these situations all have in common one thing, which is that you'd like to make predictions about a physical system whose dynamical laws are not known into every detail. So this is something that happens a lot in theoretical physics at the moment and in experimental physics, because experiments are kind of getting close to the point where we can test a regime where some people claim quantum theory doesn't apply. And this is because the objects that we can manipulate in the lab are going close to some kind of mesoscale, which is not that of microscopic particles like neutrons, electrons, and stuff like that, but it's closer to molecules, organic molecules, and even particles like viruses, which are much more heavy than these elementary particles. And some people, there is this famous Girardi and Penrose kind of theories where they claim that quantum theory should stop applying at a certain scale. And so the famous collapse of the wave function should happen. This is the case where the laws of reversible quantum theory stop applying, the superposition principle stops applying, and you do see a classical world after all. So we are getting close to the domain where we can test this type of regime. And there you have something like a quantum probe, like an elementary particle, interacting with this larger object, which could be a large mass, a large molecule, and so on. And you really don't know whether the combined system will or not obey quantum theory. So if you want to make a prediction for an experiment, you can't quite use quantum theory to describe the whole thing, because you want to see whether quantum theory applies or not with the test. But what you can do is still to apply certain general principles that don't assume dynamics to be fixed. And these principles that we came up with in this constructor theory of information and constructor theory of probability are applicable in this case. And so this is the base of a number of recent articles I've been writing with this other physicist called Vlatko Vedro, where we were looking at ways of saying, okay, we've got a system with a complete quantum dynamics. We've got some other system that we don't know really what dynamics obeys, but we know, let's say, it's got some information variable. What can we say about the composite system, and can we actually infer something about whether or not the other system, the mystery system, has got to also have some quantum features or not. And this led us to propose together a very nice experiment to test whether or not gravity has quantum features. So this is kind of the end point of one of the applications that came out of these two initial constructor theory papers. This test for quantum effects in gravity was also proposed with along independent lines by a team in London. They proposed a similar test which didn't have the same sort of underlying information theoretic reasoning. But basically the way we arrived at it was to follow this logic of what can we say about a system where a quantum particle is coupled with gravity. We know that gravity is another example of a system which, when coupled to quantum systems, we don't know how to make predictions, because there are all sorts of proposals for quantum gravity, but they're not quite, they're still controversial and there isn't a unique proposal. So we don't know which one to use. And so we said, okay, let's assume something minimalistic as for the dynamics, and let's see whether these constructor theoretic principles can lead us to make some conclusions. And turns out there is a way of witnessing non-classicality of the gravitational field by probing it with two quantum masses. And I can tell you about it at some other point, but basically that's an important application that came out of this work. And this is currently being investigated quite deeply by some quantum gravity experts, by some experimentalists who would like to also try to realize the experiment, and by this other team in London led by Sugato Bose, who they're also kind of, we're actually collaboratively trying to find a way of realizing this experiment, which would be really cool. Because this would tell us ultimately whether a classical theory of gravity is viable or not. And if it's not viable, then that means that actually it's the first experimental confirmation of the fact that, Einstein's general relativity and all of the other classical theories of gravity do not work when coupled with a quantum system, which is kind of cool. So that's, I think, the end point. That's one end point of applicability of this information theoretic constructor theory. Another thing that I'm also developing now is to try to come up with a quantitative generalization of all these concepts that are present in quantum information theory using this more general framework where we don't even use the dynamical laws of quantum theory. And this is something I'm currently doing in collaboration with this mathematician, and this is likely to provide a structure for possible candidates, to propose possible candidates for a theory that kind of is the successor of quantum theory. Of course, this is kind of 10-year plus from now. I mean, it's not something that will happen tomorrow, but I think that's the big aspiration that I have with this work. And so this is basically the one of the directions that came out of the constructor theory of information. Does this answer your question?
Yes, definitely. Thank you.
Cool.
Good to know that, it's a 10-year plan. Although, to be fair, you can't predict the future of knowledge, right? So maybe it'll take you a month.
That's right. We don't know, actually. That's true. Yes, it's a good point. Yeah, definitely.
Or it could take you, a century. But anyway, optimism. Switching a little bit from what's currently considered fundamental physics, which clearly you've been working on, I'd like to talk a little bit about the fact that constructor theory seems to bring in these emergent concepts into fundamental physics, such as you spoke about, information and computation, and also life. So what would you say to presumably the critics out there of constructor theory that basically say fundamental science and fundamental physics should be reductionist in nature, and that it should explain large objects in terms of small objects?
Yes, I think this is so as I said at the start, the best way to counteract this criticism is to show that constructor theory can address some of the problems that the other approach cannot address. So in fact, constructor theory was conjectured precisely because we wanted to try out a way of addressing some of these problems that the purely reductionist approach seemed to struggle with. And well, one being, as I said, the initial condition problem. Another being, how do we incorporate these laws of thermodynamics into the picture, given that they are very successful, but actually they're not quite compatible with the underlying dynamics as far as they are formulated now. So are they actually fluffy laws that we don't really need, which is probably what the reductionists would say? Or can we provide better laws formulated in a way that they not only are compatible with the dynamical laws that we know, but can provide future directions for finding future laws? And so the best answer, as I said, is to that criticism is, well, look, I mean, if you didn't get constructor theory into the picture, in this particular case, you would miss out on explaining physical reality. And of course, they could always say, well, I'm not interested in that aspect. That's a possible answer. I see that kind of answer, and that's fine. But on the other hand, I think physics should be very opportunistic in a way and not have preconceived ideas about what is it that it should apply to and what not. In fact, the very beauty of physics is that it is supposed to, well, physical laws are actually supposed to apply to everything we know in the universe. And it seems to me rather unscientific to say, well, look, I'm gonna study this system up to here, and then all of these other phenomena I'm gonna label as irrelevant because I think they are not quite proper subjects for physics. I think we have to work the other way around. We have to say something like, okay, we've got this interesting problem, and it seems like the dynamical laws can't quite address it. Can we find a better way of addressing it? And if there is one, let's go with that. I mean, in the same way, I'm very happy to see, and that's actually what I'm trying to find out, whether constructor theory works or not. And if it doesn't work, first of all, this will teach us a lot about physics, because it won't work for a certain reason, and that will be very interesting, because most of these principles that constructor theory is based on are actually underlying our current dynamical laws, and therefore, if constructor theory fails, there's a kind of deep bug into the whole of physics itself. So that would be an interesting fact to learn. And then I would try, I would suggest that someone should try to find out a different approach, because if those problems are still there and the reductionist approach can't solve them, I would still want to solve them. Mm-hmm. For instance, there is this idea that, I can give you, so one specific example where the reductionist purely dynamical law approach can't quite provide predictions is the current state in physics, where, as I said earlier, there are two theories which are dynamical laws that we trust and love because they've been confirmed experimentally so far in their own respective domains. However, they don't seem to agree on fundamental aspects of physical reality. For example, quantum theory says that there is an absolute time. It's very Newtonian in this sense, whereas GR or even special relativity say that there isn't such a thing, and that so in this sense, the two theories are profoundly incompatible. In addition to that, quantum theory says that the observables are not all measurable with the same accuracy by the same machine, whereas general relativity is a classical theory in that sense, because you can measure all of the observables with a single machine and you don't violate any Heisenberg uncertainty principle. There isn't such a thing there. Okay, so that now we don't have experiments that can probe the area yet where the two clash directly, because it's too far technologically speaking. So we can't get new evidence in that area to say what to do. We do not have obvious ways of varying the theories by making a small variation. Like, you add a term in the Einstein's equations and you get something that makes no sense at all. Therefore, one way to proceed is to use these principles, because the principles of thermodynamics, the principles of information theory, and these new principles that we are hoping to be able to provide now, that we've already been suggesting, would be applicable to systems that are that kind of are at the interface between GR and quantum theory, without committing to a particular dynamical law for them, which is a thing we can't do because we don't yet know exactly which law we should apply there. And this is an important gap in the current approach, which constructor theory can already help with. So that's one example where I think being strictly reductionist and sticking to dynamical laws kind of approach doesn't help. Another one is this one about the initial conditions that I said. We don't have a solution to that yet, but we are hoping that this approach might be helpful. And another one is this one where there are a number of phenomena like life and consciousness and so on, which currently are, they are bound to be compatible with reductionist view of reality, with, let's say, dynamical laws and stuff like that. From, the fact that my brain is thinking now is perfectly compatible with the fact that it's made out of atoms, and that my thoughts are hopefully a configuration of those atoms at a certain point in space and time. However, we don't really know what consciousness is. It's not, there are all sorts of proposals around, but it isn't clear. We don't yet have a theory of how knowledge is created in the brain, how we can, let's say, emulate that process. This is the AI enterprise and so on. And I feel that if theoretical physics keeps dismissing this problem as being something that we are not interested in because it's anthropocentric or things of that kind, we will miss out on explaining an interesting phenomenon in nature. So I think brains in humans and in other creatures that maybe we haven't yet met, life in the universe or something like this, intelligent life in the universe, are an interesting phenomenon that's happening because it's producing a number of things that have characteristic properties like resiliency, capacity of modifying the environment in ways that are unpredictable and robust. And I think physics has to come up with a theory about these things. A theory that, for instance, says, what are the limitations of this process? Is it a process that has some laws of, of how it should increase in time or not? Do we have a way of understanding what is it that causes the process? Why is it that some type of brains which are actually designed almost in the same way as apes' brains can come up with far more creative thoughts, which is our brains at the moment, whereas the apes' brains are also thinking in a certain sense, but they're not quite producing the same level of technology and development that our civilization has reached. So why is it that, how come all of these differences clearly cannot be the hardware, because the brains are quite similar? So what is the additional thing? And I think so Constructor here doesn't certainly have an answer to that, but it provides some tools to address the question in an objective scientific way. And I think that's what physics should be doing. I think physicists should try to understand that thing instead of saying, no, we're not going to look into that because it's, it's something that it's an anthropocentric problem. We are not going to look into that problem because it sounds to us like violating the dogma about physics being not about humans. The point is that this is not about humans. The point is that it's a thing that's happening within civilization, and it's an interesting phenomenon. And so a physicist should just be interested in it, never mind whether it's human or not. It's a bit like saying, no, I'm not going to look into optics because it's a thing that happens in human's eye. That's not a way of reasoning. So it's not a good argument to deny interest in these kind of problems. However, if reductionists are taking the stance that they don't want to look into these problems, that's also fine. I understand that view. But in my opinion, it seems to me that they're missing out. So I think I'm for an objective, rational approach to problems. And if there is something that I can't explain or I don't understand, I want to use any tool at my disposal, intellectual tools at my disposal to address the problem. And if it comes from reductionism or not reductionism, a different approach or something that I've never seen before, but I see that the thing works, I'm just going to go for it. And I think that's what constructive theory is about, is just suggesting a new set of tools which may or may not work, but they seem to be working to some degree at this stage, and we want to give it a try, a full go, I think. Yeah.
This segues perfectly into my next question. So constructive theory seemingly has provided an exact definition of knowledge, namely information with causal powers, or I think of it as information that once instantiated tends to cause itself to remain so.
Yes.
Correct me if I'm wrong. So given that, I mean, that seems promising. Do you think that there will eventually, from constructive theory or maybe another theory, be such corresponding exact definitions for things such as life or free will or consciousness? Or do you think it won't be constructive theory that explains or defines these things, but rather some other theory?
Well, I think it's not going to be constructive theory only because it should be constructive theory merged with some other tools, either from, I mean, certainly from epistemology, certainly from theoretical biology, and presumably also from neuroscience in some sense. But the thing that seems to me important is that constructive theory might provide a foundation for a theory of knowledge and therefore consciousness or creativity or whatever, whichever word you want to use for designing, for defining this set of phenomena that are happening in an intelligent life kind of scenario. And the promising thing about the tools is, as you said, that they provide an objective handle on these concepts. One thing that I feel is mostly missed by, well, it's something that repels scientists at this stage, or at least physicists, is that when you talk about consciousness, you enter a territory where words are very fuzzy, so people don't know exactly what they mean by talking. You know, the very fact that there are 10 words, maybe or more, to define that are used nowadays to define what people might call consciousness or creativity or whatnot is a sign of the fact that we are very confused about this.
Yes.
And so a physicist doesn't like this. I mean, physicists are into laws that are exact and precise and mathematically formulated in a way that they make absolutely tight the concepts that they define. Of course, we don't have yet that thing for consciousness, but if we could use some of these notions rooted in constructive theory, let's say the knowledge notion, to construct such a theory, well, this would be a great step forward, because we would be talking about something that at least is objective and doesn't necessarily refer to sentient beings, knowing subjects, things that seem, to be fair, actually not very scientific sometimes. So I think at the moment, constructive theory does not at all solve any of these problems, but what it does is that it provides the basis, the conceptual basis or foundations for a theory of this concept to be constructed. And this is relevant for, going back to this issue that von Neumann was trying to address. This is relevant for the universal constructor. And it's intimately connected. And I think, well, David has some writings about this, and I've been thinking about it as well in various ways. But what's currently known about all of these things is that, so it seems that the laws of physics as currently known permit the existence of a universal computer. I mean, we don't know if this is possible really, but we don't know of any impediment to the construction of a machine which can perform all of the computations that are physically allowed. And this is the famous universal quantum computer. And people are now racing towards it. I think that there is this race between Google and IBM and Microsoft, all these giants that are trying to kind of crack this, the construction of this machine. So, all right, that's the universal computer. Now, the fact that there can be universal computation is something that, well, it's actually a very peculiar fact of the laws of physics. But now you can think, as I said, of upping the game and thinking of, okay, what about if instead of thinking of a machine that can perform all permitted computations, I want a machine that I can program to perform all permitted tasks. And that's the universal constructor. And universal constructor is a programmable object, so you can still write a program in it. But basically, instead of just doing computations, it's going to harness all of the materials and resources to also perform tasks that transform physical systems into other physical systems. So it will, for instance, include all of the repertoires of heat engines, of refrigerators, of nanomechanical devices that can deliver drugs in the body, or there is other types of machines that we are currently using in our technology. This machine should incorporate the repertoire of all of those into itself. And it should have this other property, which is very important, which is what von Neumann was struggling with. It should be capable of recreating itself out of raw materials. So it should be able to self-reproduce. So it should contain a recipe that should allow itself to reconstruct the whole of the universal constructor and then put this recipe inside the universal constructor, just like living systems do. And so, okay, we have a very fluffy understanding of how this object should operate. Von Neumann tried to lay some foundations, but then he didn't succeed because he tried to embed this into cellular automata, and this was not quite. It was a kind of the start of a very detailed search in a direction which didn't provide general principles for the universal constructor. And I think constructor theory will provide a set of principles under which we could, for instance, show or not that the universal constructor can exist. And this would be very interesting because it would at least put the universal constructor on an equal footing with the universal computer. And at the moment, we don't even have that. So I guess that's very promising direction, because the universal constructor is still not a sentient entity, of course, because it's a programmable entity, so it doesn't have a will of itself, but it is much more general than a universal computer. And then there is this phenomenon that's happening with intelligent life, with humans or possibly other creatures around in the universe. And well, one fruitful question is, how is a human being different from the universal constructor? So is it more powerful? Well, yes, it should be, because it can come up with new ideas, and universal constructor can't, because it can only produce things that you program it for. But on the other hand, there are all sorts of intuitions that we don't know yet how to address. But I think having a theory of the universal constructor, which is something that constructor theory will ultimately provide, will be a very important underlying conceptual tool to tackle the problem of understanding consciousness and so on. And so I think all the more reasons to try and deliver some nice general principles that hold irrespective of the scale of the system that you look at and of the dynamics, because then these principles will be able to underlie even a theory of consciousness, hopefully.
Yeah. I never thought about it contrasting people with a universal constructor. Interesting. Okay, so we only have 5 minutes left, correct?
Cool. Yes, that's right. Yeah, I'm sorry about it, but yeah.
No, yes. This has been great. So maybe I'll just ask you one or two more questions, maybe one. Is there anything you haven't said about what you're currently trying to solve that you'd like to address?
No, I think another thing is to try to work out. So another work that I did was to propose these laws of, so I wrote a paper where I generalized some of these ideas of existing thermodynamics, this approach called the axiomatic approach to thermodynamics, where you say the second law as stating, let's say, that a task of changing a state of an object from A to B is possible, but the task of changing the state from B to A is impossible. So you state the second law that way. And so in that sense, the second law stated that way is more easily reconcilable with laws of dynamics that are time reversal symmetric, because the fact that the elementary particles of which your objects and machines are made obey time reversal symmetric laws is not in conflict with the fact that at the higher level you have a task, A goes to B, for which you can create a constructor that facilitates the processing in one direction, but it does not work for the opposite direction. So there is no constructor for going from B to A. And to explain to you with an example, this was already known since Joule and his work on thermodynamics. If you have a glass of water which is perfectly isolated from the environment and you want to heat it up by stirring it, so you put a stirrer inside and you start stirring, you can do that. So there's a constructor that by using some energy can stir the volume of water and heat up the thing. But if you would like to do the same to cool the glass of water, you can't. So it's impossible to cool a glass of water just by mechanical means, by stirring only. You can cool it, of course, by putting it in touch with a larger environment which is colder, stir it, and then some molecules of air from the environment will bounce off the surface of the liquid, and this will cool down the liquid. But if you have a perfectly isolated object which is only interacting with the environment through the stir, you won't be able to cool it down. And so this was already known at the time, but you can generalize this statement in constructor theory in a way that, first of all, doesn't mention stirrers, liquids, volumes of water, temperature, but it amounts to generalizing the second law to be scale independent and to apply to systems that don't necessarily have a temperature, etc. And I think this was some work that I did a few years ago. And now I'm trying to work out the consequences of this, because in parallel in physics, there's another thing that's happening, which is called quantum thermodynamics. And this is an enterprise where people have tried to generalize the laws of thermodynamics to quantum systems. So they put together second law and quantum dynamics, and they try to see what happens there. And of course, they did it very nicely, but I think they still assume a specific dynamics. So it's not the thing that they came up with is not as general as you would like a theory of thermodynamics to be, because you would like it to apply to a reasonably wide set of dynamics, not just to quantum systems. So what I'm aiming at the moment, and this is done in a collaboration with a postdoc, that we are trying to merge this approach from quantum thermodynamics, which fuels microscopic heat engines and so on, with the approach from constructor theory. And I'm also planning some experimental demonstrations with some people in Sheffield and in Singapore to show what is the difference that, if any, that constructor theory provides to the existing laws in terms of defining work and heat. And this is nice because if there is a difference, which is what we expect, knowing what work and heat are in a classical heat engine allows you to work out, for instance, the efficiency, the power of it, and power effectively the part of the Industrial Revolution a long time ago. Now we have these nanoscale devices which can compute and so on. And if we could see them as heat engine as well, as heat engines as well, then we would, and if we had principles that applied exactly to them, we would also be able to work out all sorts of other consequences about the limitations of their power, about how to extract more work out of them if possible, and stuff like that. And I think that's one big line of development that I hadn't mentioned before, which is quite exciting. And hopefully it also allows us to connect constructor theory to existing enterprises, which should be kind of fruitful for both constructor theory and these existing other efforts. It would be nice to merge them together to make them more powerful.
Okay, well, thank you very much. So it seems like you're slowly getting more scientists working on the theory. If you had, in other words, if people are interested in working on constructive theory but are not at the moment, say they're working on something else, what would you say to them? Are you actively recruiting scientists to work on constructive theory? What are you in that stage?
Yes, so I think there are certainly all sorts of open problems that both David and I and these other, Vlatko and other people that I mentioned earlier are, that we have found as we were trying to apply constructive theory to various things. And these open problems are just waiting for someone who is interested in them to address them. And so at the moment, I've got a number of PhD students who are asking me to work on these issues. So that's very nice, actually. There's a new PhD student joining in the fall here in Oxford who will be doing something about constructor theory and category theory and stuff like that. And in general, yes, there are interesting open problems that are kind of cutting across various disciplines. So thermodynamics, post-quantum theories, quantum information, and even this emergence of dynamics problem. Possibly even theoretical biology, which is something that I started actually discussing it with you at some point. And then I also had a few discussions with Sarah Walker at Arizona State University. And there are some complexity theorists in Singapore CQT who are also interested in this. So there are all sorts of kind of open problems. And I think, yeah, I'm happy to, actually, I'm trying to recruit people working on this. And I'm expecting with these experimental demonstrations there will be more interest coming along as well. So I think Definitely. I'm sort of recruiting people. It's all a question of, depends on how much money I have available. But let's say for, ideally having infinitely many resources, I'd be very happy to have more collaborators.
Great. Well, I don't want to make you late for your next thing. So thank you, Chiara, very much. It's been a lot of fun. It's been a pleasure. Have a good one, Chiara.
Yeah, thank you so much, Brad. Take care. Take care. Bye.